Welcome back, students. In the past lectures, we have previously discussed ideal solutions. These are solutions that obey Raoult's law. We're going to look today at solutions that no longer obey Raoult's law and try to describe them as best as we can. The learning goals for today are going to be to apply Henry's law, which is a law that goes alongside Raoult's law. We're going to want to be able to describe and calculate partial molar volume, which is something that real liquids do when they mix. We'll define activity, which is basically fugacity, but for liquids and solutions. And then we'll be able to calculate the equilibrium constant for reactions in dilute solutions. So we'll start by looking at how solutions deviate from Raoult's law. As a reminder, Raoult's law is that the pressure of a substance in a solution is equal to only the mole fraction of that substance times its vapor pressure. For a solution to obey Raoult's law, the components of the solution must have identical interactions between themselves and the other components. So the solute-solvent interactions need to be the same as the solute-solute and solvent-solvent interactions. If you tried, you could probably come up with some solutions that would likely obey Raoult's law. Some examples we've seen are things like benzene and toluene. Maybe you'd think something like hexane and pentane and so on. However, such an attempt would also show you that very few solutions would even come close to obeying this law. So we've already seen one example with benzene and dichloroethane, where it does a pretty good job, and the predicted Raoult's law on the dashed lines here pretty closely matches the solid experimental line. There are plenty of solutions for which Raoult's law doesn't work at all. So we can see an example of acetone and carbon disulfide here. And you can see that these basically never follow Raoult's law. Since every substance is different, it is very unlikely that any two substances would interact in such a way that they would both obey Raoult's law. We can see that this solution deviates very strongly from Raoult's law. So Raoult's law is not going to be able to explain this solution, and we have a non-ideal solution. What then are we to do? Are we wholly unable to explain these kinds of solutions? Before we panic too much, we should stop and take a look at the graph. I want you to pause the video here and look to see if there are any regions where Raoult's law applies. Hopefully, you found that there are actually some regions where Raoult's law applies. Raoult's law is going to apply where the data in the solid curves is pretty similar to the dashed lines. And so we can see for low mole fractions of carbon disulfide, the acetone curve pretty nearly matches Raoult's law. And then once we get, say, above 0.1, it begins to deviate, and deviates quite strongly for the remainder of the curve here. At high mole fractions, the carbon disulfide peak matches Raoult's law. And then at lower mole fractions, it deviates very strongly. So what do these things have in common? At low mole fractions of carbon disulfide, acetone is the solvent, and acetone is obeying Raoult's law. At high mole fractions of carbon disulfide is the solvent, and carbon disulfide obeys Raoult's law. So even for this very non-ideal solution, we can see that when one component can be very clearly said to be the solvent, that is when its mole fraction in solution is approximately greater than 0.9, it obeys Raoult's law. Note that Raoult's law does not apply to the solute under these conditions. So when acetone is the solvent, carbon disulfide is deviating very strongly from Raoult's law. And when carbon disulfide is the solvent, acetone is deviating very strongly from Raoult's law. Why is this the case? Raoult's law assumes that the solute-solvent interactions are the same as the solute-solute interactions. Since this is in general untrue, Raoult's law doesn't apply. However, under these dilute conditions, what are our solvent and solute interacting with? If the solution is almost exclusively acetone, acetone molecules are essentially only interacting with acetone, and therefore they will deviate based on Raoult's law, because the things that they are interacting with are the solvent. where the carbon disulfide won't deviate because it's not interacting with carbon disulfide as Raoult's law predicts, it's interacting with acetone. And the same is true for the other end of the equation here. So what this implies is that the vapor pressure of the solute is dependent on its concentration and the strength of these solute-solvent interactions. And we can actually see that here we have a linear relationship, again, under conditions where here acetone is the solvent. So carbon disulfide isn't leaving the solution based on interactions with itself, but based on interactions exclusively with acetone. These are different, but they're also only with acetone, so we can get a different line here. And we'll fit this line to a linear curve here, and this will give us a new law that will describe ideal dilute solutions. Solutions like this of acetone and carbon disulfide can be said to be non-ideal. They're deviating from Raoult's law. And that means that in general, these things that used to be true for ideal solutions are no longer true. So the free energy of mixing is not always less than zero, and the entropy of mixing is not always greater than zero. If we actually have a solution form, that's going to be the case. But we can see, and we'll talk about this later, a change in enthalpy of mixing, meaning the liquid molecules interact differently than they do. And we can also see a change of volume upon mixing, and we'll describe this in a couple of slides. So Henry's law tells us that if we are in the limit where one component of a solution becomes the solute, so it has a very low mole fraction, its partial pressure follows a different linear slope than when it's the solvent. It has the exact same form as Raoult's law. So Henry's law tells us that the partial pressure of our component I in solution is equal to the mole fraction times now this Henry's law constant. This Henry's law constant is a fill-in for the vapor pressure. It's kind of like what the vapor pressure would be if we were interacting only with the solvent instead of the solute. So this vapor pressure, or this Henry's law constant, is solute and solvent dependent. So something like acetone and carbon disulfide will have a different Henry's law constant than acetone and water, or carbon disulfide and water, or ethanol and acetone. They're all dependent on the solvent themselves and the solute that's interacting with the solvent. And here we can see that we have a pretty linear relationship under both regions. So when carbon disulfide is deviating strongly, we have a linear relationship for small mole fractions. And for acetone, we have a linear relationship for high mole fractions. For middling mole fractions, neither Henry's law nor Raoult's law are going to apply because we don't only have one kind of interaction. So both of these laws hinge on the fact that the solute and the solvent are interacting primarily with solvent. If we're in the middle of this region, that's not true, and we can't use either of these laws to very accurately predict what's going on with our solution. This leads us to the ideal dilute solution model. Solutions in which the solvent obey Raoult's law and the solute obeys Henry's law are known as ideal dilute solutions. In these solutions, every molecule approximately only interacts with the solvent. Under conditions where the mole fractions are approximately equal, this approximation does not hold. That would be in these middle regions. And the solution cannot be described by the ideal dilute solution model as it is no longer dilute. We might ask ourselves, how applicable is this model? Let's consider a solution in water. The concentration of water is 55.5 moles per liter. That simply comes from the fact that 1 mole of water is 18 grams, and that is approximately 18 mils. So how concentrated would a solution need to be to exceed this mole fraction of 0.1 where the ideal dilute solution model doesn't work anymore? And for this, we had to be approximately 10% of 55.5 moles per liter, which is 5 molar. In your chemistry career so far, I doubt you have worked with very many solutions more concentrated than 5 molar. This line of reasoning suggests that most solutions are dilute enough to actually satisfy this model. Of course, many are not, such as a 70% ethanol solutions and other types of solutions that you may have used that have 2 significant fractions of liquids. If we consider these kinds of solutions that are interactions between two molecules, the solute and the solvent, that are different than the solvent, or solute, something strange emerges. When two liquids are mixed, and this is especially true if they're in near equal concentrations, they undergo a change in volume upon mixing. This means that if we mix 10 mils of water and 10 mils of ethanol, the resulting 50% ethanol solution would not have a volume of 20 mils. Why does this occur? To straighten this strange observation out, we simply need to consider why liquids occupy volume in the first place. The liquid molecules physically interact with each other and take up space. If we change the type of molecules that are interacting, we're going to change the ways in which they interact and the amount of space they need to occupy while interacting. So they will physically take up a different volume. The change in molar volume is typically small, on the order of a fraction of milliliter per mole. We can describe the molar volume in the same way we did for the chemical potential. In fact, the chemical potential is the molar Gibbs free energy. We use a little bit of different notation for molar volume. So we'll use the volume with this bar on top of it. And this describes the partial molar volume. This is the volume by which a solution changes when 1 mole of substance is added at constant composition. So we can see here for our acetone and chloroform mixture that the volume of acetone will change and the volume of chloroform will change as a function of the mole fraction. And we can describe this in exactly the same way as we've described the chemical potential. So we can say that the partial molar volume is a function of pressure, temperature, and moles of substance 1 and substance 2. Often pressure and temperature are constant, but we can have this change of partial molar volume being equal to the change in volume as 1 mole of substance is added at constant pressure, temperature, and number of moles of substance 2. And we achieve a constant moles of substance 2 by having a much larger number of moles of substance 2 than substance 1. The total volume is then simply the number of moles of substance 1 times the partial molar volume of substance 1 and the number of moles of substance 2 times the partial molar volume of substance 2. And we can see a relationship here that when acetone goes up, chloroform goes down, and when chloroform goes up, acetone goes down. This can be derived from the Gibbs-Duhem equation that we saw before in an analogous way. So instead of the chemical potential changing by the ratio of the mole fraction, now the volumes are changing by the ratio of the mole fraction. So as the molar volume goes up, partial number 2 goes up, the molar volume number 1 will go down, and the extent of that depends on the mole fraction. The fact that the volume changes is indicative of the fact that the concentration of a component of the solution changes as a function of mole fraction. To account for this, we use the activity and the activity coefficient. Activity is essentially the same as fugacity, but for solutions rather than gases. So we can say that the activity is equal to the actual partial pressure over the vapor pressure that it would be. And we can also say that the activity is equal to the mole fraction times gamma, which is the activity coefficient for substance I here. So we can plug this back in and figure out that the chemical potential of the solution is equal to the ideal chemical potential plus RT natural log of this activity coefficient, which is the mole fraction times some correction. So if we don't need the correction, the activity is the same as the mole fraction, but we often need this correction here. We also often don't really want to think of these in terms of mole fraction, but rather think of them in terms of some other unit of concentration. And we can represent the mole fraction based on the molality. Remember that the molality of the solute is the number of moles of solute divided by the mass of the solvent in kilograms, which is simply the number of moles of solvent times the molar mass of the solvent in kilograms. The mole fraction of the solute is the number of moles of solute over the number of moles of solute plus the number of moles of solvent. If we divide by the number of moles of solvent times the molar mass, we can end up with a mole fraction based on molality. If the molality of the solute is very small, again, if we have an ideal dilute solution, this on the denominator becomes essentially 1 over the molar mass of the solvent, and we can represent the mole fraction of the solute as simply the molality of the solute times the molar mass of the solvent. So for dilute solutions, it's appropriate for us to be able to use the molality in place of the mole fraction. This allows us to actually measure the activity coefficients for substances. So we can do something like a boiling point elevation and add in a known amount of substance and calculate how much the temperature changes. And that will give us the activity based on the amount of substance that we added. So we might say, add 1 molar salt to water, and that might predict a certain change, maybe a 20-degree change or something. But if we only get an 18-degree change, it tells us that we're not actually at an effective concentration of 1 mole, but we're at some different concentration. And so we can get a measurement for what the activity coefficient should be for that. We would like to define activity such that it approaches the mole fraction or the molality, because we can interchange them, in the appropriate limit. Now we come to a challenge that we have to determine what the appropriate limit is, and it's actually different for the solute and the solvent. For the solvent, the mole fraction approaches 1, and we would like the activity coefficient to approach 1 as the mole fraction approaches 1. For the solute, the mole fraction is approximately 0, and we want the activity coefficient to approach 1 as the mole fraction approaches 0. To do this, we need 2 different standard states. The first is the one for the solvent, and this is called the Raoult's law standard state. For the solute, we have what's called the Henry's law standard state. Now, what are these different standard states? Well, the Henry's law standard state is going to be a standard state such that the activity for the Henry's law, and so we have this H here, is equal to the partial pressure divided by the Henry's law constant. For Raoult's law, we'll have that the Raoult's law activity is equal to the partial pressure divided by the vapor pressure. And then the coefficient is, of course, can be defined in this way. Why do we do this, and what are the consequences of this? Well, the Raoult's law standard state is pretty normal. So the Raoult's law standard state is a state in which we have pure solvent. The Henry's law standard state is a state in which we have pure solute, but that pure solute only interacts with solvent. So this standard state is kind of strange and is, of course, non-existent. It's what we could call a theoretical standard state. But it's the only way that we can define these activities how we want to get them to go to the mole fraction in the appropriate limit. So what does this look like? Here we can see the activity coefficient for our carbon disulfide according to Raoult's law and according to Henry's law. The activity coefficient is gamma here. We want the activity coefficient for Raoult's law to approach 1 as we get to 1 mole fraction of carbon disulfide, and we can see that it does. But if we were to try to apply Raoult's law standard state, once we get to a mole fraction of 0, our activity coefficient is like 4. It's way off and it's acting nothing like it should. So then we need to use the Henry's law standard state for the low mole fraction cases, in which carbon disulfide is acting like a solute. And here we can see that it also approaches 1. Remember that these standard states are only going to apply if we're in this ideal dilute solution limit. So if we're at a mole fraction of 0.5, neither of these are going to apply, and they're both going to horribly miss what the actual activity is. This is because more concentrated solutions have their own complicated interactions between solute and solvent that can't simply be described by the ideal dilute solution model. The last thing we're going to do is calculate chemical equilibrium for substances in solution. You are already familiar with how to do this. It's the same as we have done before. We can say that the free energy of our reaction is equal to the sum of the reactants minus the products. This will give us a standard state condition based off of Henry's law and a correction based on the activities. Remember, the stoichiometric coefficient is positive for products and negative for reactants. So this sum here is simply the sum of the free energies of reactants minus products. We can rearrange this and determine that the free energy change under standard conditions is equal to negative RT natural log of the activity raised to the stoichiometric coefficient. And we can substitute in an equilibrium constant for the activities. For the most part, when we are working with dilute solutions, the solutions are sufficiently dilute such that the activity coefficient is 1. And therefore, the activity is simply equal to the concentration. So instead of considering the concentration or the activity, we can simply consider the concentration and plug in the concentrations here. You may not have seen this capital Pi symbol before. This is the exact same as the sum, except for instead of adding, we are multiplying. So here we are multiplying all of these concentration terms raised to the stoichiometric coefficient. So instead of the sum, which is products minus reactants, this is products divided by reactants, since having a negative here will divide rather than multiply. And that's how we can calculate the equilibrium for substances in solution. That finishes us off here for solutions. So to conclude, an ideal solution is one in which the solution obeys Raoult's law. Most solutions aren't going to do that, so we instead describe solutions as ideal dilute solutions where the solvent obeys Raoult's law, but the solute obeys Henry's law. If we have a non-volatile solute that will cause changes to the solvent based on the concentration of the solute alone, this gives us colligative properties like boiling point, elevation, freezing point diffraction, and osmotic pressure. And then we can, of course, calculate the equilibrium for solution phase reactions. In the next lecture, we are going to look into electrolyte solutions and see how electrolyte solutions differ from these solutions. And actually, they're easier to describe because we have long-range solute-solute interactions that come from the positive and negative charges that let us apply a more uniform model to them.